Every second, global industries like healthcare, finance, and government generate massive volumes of raw data. The physical infrastructure required to process this information is reaching a point of extreme strain. For decades, that workload fell to the Central Processing Unit, or CPU. It was designed to be a brilliant general-purpose orchestrator, capable of switching between a wide variety of tasks. But the CPU has a physical limitation. It processes tasks sequentially. It handles instructions one step at a time, relying on just a few highly capable cores. It is incredibly intelligent, but it operates in a single file line. When tasked with trillions of parameters or expansive 3D environments, this serial queue becomes a physical wall. The math simply takes too long to execute on traditional hardware, causing processing to stall. To overcome this, engineers required a chip that didn't wait for one calculation to finish before starting the next. They needed a processor that could perform mathematical operations everywhere, all at once. This is the Graphical Processing Unit, or GPU. While the CPU on the left uses a few large cores, the GPU on the right uses a massive grid of thousands of smaller, distinct processing units. This architecture enables parallel processing. Instead of solving one complex problem in a line, the system breaks the workload into thousands of simpler equations and solves them at the exact same time. Shifting from serial logic to parallel logic provided the mathematical throughput necessary for modern high-volume computing. The original use case for this parallel muscle was rendering 3D graphics and supporting high-intensity virtual desktops for engineers. But enterprises soon realized that these chips were ideal for high-performance computing, where thousands of similar calculations are needed to analyze massive datasets. In this environment, heavy workloads are spread across multiple compute nodes in a server array, allowing researchers to reach conclusions in weeks rather than years. The hardware was now in place, waiting for the most intensive parallel computing challenge ever conceived. That challenge is generative AI and machine learning. These are not just software programs, they are massive mathematical workloads. Modern large language models rely on hundreds of billions of individual weights and parameters to predict the next token in a sequence. A GPU's high-speed memory, or VRAM, is uniquely capable of holding these massive model weights in memory. This allows for rapid, parallel access to the data without the system crashing. This hardware profile is the reason neural networks can process information at a scale that mimics human reasoning. But maintaining this hardware is difficult. GPU architectures move through rapid release cycles, with new chips often arriving annually. This makes on-premise hardware a depreciating asset that is capital-intensive to maintain. Cloud Strategy addresses this by providing on-demand access to virtualized or bare metal servers. It allows organizations to pay only for the compute they use, shifting the focus to output rather than hardware maintenance. Treecapital's Anven ecosystem was engineered to harness these cloud-based GPUs, specifically for the specialized needs of the enterprise. This diagram shows how Anven utilizes sovereign AI. This architecture isolates the model from the open internet within a virtual private cloud. Within the private subnet, there is no internet gateway. This ensures that sensitive proprietary data and telemetry never exfiltrate the client's secure perimeter. This framework enables enterprises to scale their processing power as needed, while keeping their data footprint strictly within their own network. Forward momentum. The final stage of this evolution is taking that massive cloud-scale logic and running it locally in the physical world. This process is called quantization. It shrinks the mathematical precision of an AI model to drastically reduce the memory it requires to run. Anven uses this technique to run 3 billion parameter models directly on edge hardware, allowing smartphones and wearables to process tasks locally. On-device inference delivers results with near-zero latency, maintaining accuracy comparable to models that require a full data center to operate. Definitive. The GPU changed the way machines process reality. Now, ecosystems like Anven have decentralized that power, placing it exactly where the enterprise needs it most.